Hello and welcome to Lecture 4A. Today we'll be looking at tuning PID parameters. So today we will learn why do we even tune PID parameters to begin with, and how to tune PID parameters the manual way or the simplest way. So why do we tune PID parameters to begin with? Well, the main reason is if you turn a motor on with no controller, that motor is unstable. And the motor probably doesn't do what you want and is a little bit unpredictable. And PID corrects this. PID corrects this. And lastly, the main important point is it actually improves the performance of a system. So PID improves the performance of the process or system. It's important to understand that you have to tune the PID parameters to get the optimal performance. Okay, and it's important to understand that you have to tune the different PID parameters to get to that optimal process. So, how do we actually tune a PID controller then? So, number one, make Ki and Kd equal to 0. That means remove the integral and remove the differential constants. Number two, gradually increase Kp until overshoot touches the set point. Now what that looks like is, if I draw a graph, get a different color. So imagine blue is our set point and orange is our signal. Now if Kp is too small, it will look like this. This is what your control output signal will look like. So Kp is too small. And if Kp is too big, it will look like this. And you'll get those oscillations. So Kp is too big. Now if Kp is just right, then Kp looks like this. So Kp is correct. It's just right. Now, if you notice, you can see that for Kp is just right, there is actually this offset here. So, how do we remove this offset? Okay, so that brings us on to step 3. Gradually increase Ki until the offset is close to the set point. Okay, I'll draw a graph and draw a blue set point. Could be a straighter set point, but if in orange, if Ki is too small, it will look like this. Like you'll still get this similar shape, but you'll gradually get to the set point. Remember that Ki is used to correct the offset caused by Kp. So Ki is too small. And if Ki is just right, Ki will cause this to happen. So you can see that if you settle at the set point, so Ki is just right. And then, as you can expect, if Ki is too big, you have an unstable system and it starts oscillating violently. And it may not actually settle properly either. So Ki is too large. And just remember that Ki is typically used for correcting steady state errors. So the offset caused by Kp is a steady state error and Ki is used to correct it. Okay, moving on to step 4. Gradually increase Kd so that the signal is smoother. Okay, so first let's draw a terribly drawn graph and a badly drawn set point. Okay, remember that Kd, the differential parameter, is used to smoothen the signal. So Kd is used to smoothen the signal. So if Kd is too small, you'll still see an overshoot and you'll still see some oscillations. So Kd is too small. Okay, if Kd is just right, Kd will actually flatten out the overshoot and then it will settle. So Kd is just right. Now remember that increasing KD actually dampens your system, so it will slow down. Now if KD is just too massive, well, KD, remember, becomes quite aggressive to rates of changes in error. So if there's a high frequency noise or anything like that, KD just starts to act erratically, but it also acts erratically to the overshoot too. So you'll find this kind of weird oscillatory behavior. So KD is way too big, and you do not want this weird kind of behavior. I mean, it will still get to the set point, but you'll have this weird oscillations that you may not like. And if KD is just even larger than that, then you'll just get this. The oscillations will just increase. It will get to the set point eventually, but you won't like your system. Okay, and finally, step 5. Any fine tuning that you want to do. So maybe you want a slower system or a faster system, or maybe you can accept a bit of overshoots and oscillations. Well, feel free to play around and fine tune your system. Fine tune the 3 variables P, I, and D. Okay, so is this the only way you can tune PID? Well, not really. There are actually other ways to tune PID controllers, such as the, whatever that name is, Nichols method, Cohen-Coons method, and model predictive control. Today we just looked at manual PID tuning, but there are better and other ways you can tune your PID controllers for different scenarios. So these methods are used in more advanced scenarios and are out of the scope of this current lecture. Okay, to summarize, today we learnt the basic steps to manually tune a PID controller. Number 1, make Ki and Kd 0. Number 2, increase Kp to get overshoot to the set point, and remember that creates a little offset for our signal. Number 3, increase Ki to remove that offset. And number 4, if you need to, increase Kd to smoothen the signal. And finally, if you would like, do any fine tuning you want. Maybe you want a faster, slower system. Whatever you need, you can do any fine tuning. Okay, finally, thank you. Next lecture will be lecture 4B, where we will be using an online simulator to show you how we can tune the PID controller manually, instead of looking at my horribly drawn graphs.